We continue with our discussion of enthalpies by looking at the enthalpy of solution. Now we all know what dissolving is, and we all know what a solution is. But I want us to therefore use our knowledge of those two terms, dissolving and solution, to come up with a definition of the enthalpy of solution. Now we realize that in dissolving there are two important things that you have to take note of. One of them is the amount of solid that we are dissolving, what we will call the solid. How much solid are we dissolving? And of course, as far as we are concerned in chemistry, we give quantities in terms of the mole. Now the other parameter that we have to take note of is the amount of solvent. The amount of solvent that you are using. Now we can try an experiment, and you can do this in the lab. Now I did take some sodium hydroxide. So okay, I took 4 grams. There's no reason why you cannot take 10 or whatever the amount. Then I dissolved these in 5 cubic centimeters of water. That was a bit difficult, so I added 15. Then I got some very big rise in temperature. It's fun to look at that. The thermometer, there is a big change in temperature. Then I allowed that solution to cool. Then I added some 5 cubic centimeters of water. Now what was I trying to see? Did I get all the possible amount of energy when I dissolved the 4 grams in sodium hydroxide? So I was expecting that when I add 5 cubic centimeters of water, of course they will be at the same temperature, say 22 degrees Celsius, because I'll allow this to cool, and this will be at 22 degrees Celsius. When I added water, I was expecting the temperature to remain constant, because I should have gotten the maximum amount of energy that is possible to get. But to my shock, there was a further rise in temperature. In fact, my solution rose from 22 degrees Celsius to 24 degrees Celsius. And maybe if I continued, I allowed that to cool again to 22 and added water, I would get a further rise in temperature. Of course, that would not be 24. So I was keen to know what is happening. I discovered that whatever energy I'm getting this process is what I call the enthalpy of dilution. So I can continue adding water, I'll continue getting more and more of the enthalpies of dilution. But it's going to come a point where further addition of water will not lead to any significant rise in temperature, rise in this case. So that solution is going to be said to be infinitely dilute. So I get a solution that is infinitely dilute. I have gotten to a point of infinite dilution. So a solution is going to be said to be infinitely dilute if addition of more water does not lead to any further change in temperature. And it is that at that point then I'll talk of the enthalpy of solution. So the amount of solvent chosen is not a liter as we did in the mole, not 100 grams as we did in solubility. I'll add so much water so that I can get an infinitely dilute solution. So when I get to that point, then I can talk of the enthalpy of solution of a substance. So what therefore becomes our definition of the enthalpy of solution? And you can be thinking of one, so you must remember to include two things: the amount of solid that you are dissolving, that is the solute, and the amount of solvent that you are going to use. And what is the amount of solvent? So much that you get an infinite dilute solution. So the enthalpy of solution is going to be defined as the enthalpy change. The enthalpy change when 1 mole of a compound is dissolved to make an infinitely dilute solution. 1 mole of a compound is dissolved to form an infinitely dilute solution. So you are going to add so much water that whatever solution you're going to get is going to be a solution of infinite dilution. Now there are two ways, therefore, we can therefore calculate the enthalpies of that solution in two ways. You can calculate the enthalpies using the Hess law. Remember the Hess law? The amount of energy produced or absorbed during a reaction is independent of the path. So you can use that to determine the enthalpy of solution, and we shall see how that will apply. Or you can experimentally determine the enthalpy of solution. Allow me to just take us one step further or one step behind. That note I've said it is an enthalpy change. What does that mean? Now I don't want to commit myself to energy produced or energy absorbed. Why? Because dissolving can be either endothermic or exothermic. So it is the energy either absorbed or the energy produced. So you can simply say the energy change when 1 mole of a substance is dissolved in such an amount of water to make an infinitely dilute solution. Now let's start our discussion, therefore, after defining by calculating the enthalpy of a dissolving using the Hess law. Now for this purpose, we are going to consider dissolving to consist of two processes. One, the force of attraction between the ion will have to be broken. So if I start with the sodium chloride, now for instance, the particles are so close to each other, there is maximum force of attraction between the ions. So the sodium ions and the chloride ions. So what will happen? On the surface of the crystal, water molecule is going to interact in such a way that the hydrogen pulls the chloride. So there is an attraction between the chloride and the hydrogen ions in water. There is a force between the positive and the negative. And that leads to the freeing. So this chloride ion is now removed from the crystal, from the lattice. It is removed, it's now separate. So what we are saying is that the force of attraction between the sodium and the chloride ion has now been broken. What breaks that? The force of attraction between the water molecule and the ion. So it pulls. That interaction rate can be said to pull that so that the ions are now free. They are so far apart. So we can now say that from the solid sodium chloride, we have gaseous sodium ions and chloride ions. What do you mean by gaseous? What we are saying is that the ions are so far apart, there is no force of attraction between them. The force of attraction between the sodium and the chloride ion has now been broken. They are very far apart. Now to do that, of course, you require energy. The energy that is required for that is called the lattice energy. But from our books of experimental data, the lattice energy is going to be given as negative. Why do we give it as negative? Why? Because by definition, lattice energy is the energy produced when 1 mole of an ionic compound is formed from constituent gaseous ions. So it is, in this case, we are not forming. In this case, we are breaking the force of attraction. But from definition, it is supposed to be the other way around. So that should not confuse somebody, because Ratti's energy is always going to be given as negative. It is the energy produced when 1 mole of an ionic compound is formed from constant gaseous ions. So like in the case of sodium chloride, it is the reaction. It is the energy for sodium plus chloride ions to form sodium chloride in solid state. So, but you realize now we are going the reverse direction in dissolving. So that's the first process that is involved in dissolving. Also, so theoretically we can say when a substance dissolves, the first thing you'll have to do is to break the ions. Let them be so far apart, there is no force of attraction between them. What is the next thing that happened in dissolving? Now, this is the next thing that will happen when you dissolve substances. So the sodium ions so formed will be surrounded by water molecules in such a way that the negative ion is attracted. Okay, it's partially negative. The sodium, the oxygen is partially positive, negative because of the electronegative nature of the oxygen. So that negative is attracted to the sodium, and then the sodium ion is surrounded by water molecule. We say that now the sodium has become aqueous. So the process is called hydration. Let's look again at the chloride ion. Now we have the partially positive hydrogen ion attracted to the chloride because the chloride is negative. So a bond is being formed. Now the chloride ion changes from gaseous state to the aqueous state. So it is said to be hydrated. Note that this is a bond formation process. Therefore, energy will be given off. So there are therefore two processes in dissolving. One that will involve energy being added to break the ions apart. Then energy being produced so that the substance becomes hydrated. That energy is called the enthalpy of hydration. Now, of course, you realize that the amount of energy that will be produced during that process will depend on the charge and the size. Like, I think the hydrogen energy of aluminium is something to the tune of 4,000 Kelvin. So that is very high. Why? Because of a very big charge on the aluminium on a small ion. So the force of the bond form becomes very strong. It's a very strong bond. So now the relative amount of the enthalpy of solution therefore will depend on the relative quantities of the two. And we come up with a very interesting observation that when you dissolve gases, you are always going to dissolve gases exothermically. Why do you think that is so? Right? I hope you are thinking, like I think you are, that the force of attraction between gaseous molecules is zero. Now that you need to break the force of attraction between the molecules, and the force of attraction is almost non-existent, then after you've gotten the molecule, you're surrounded by water molecules. What does that mean? This is zero. Energy required is almost equal to zero, but energy produced is now some energy is going to be produced during the hydration. So there is only one energy in dissolving molecules for all practical purposes. Only one energy is involved, and that is the hydrogen. And hydrogen has always to be, hydrogen must always be negative. Energy is going to be always produced. Now another very interesting observation is this one. When you dissolve anhydrous copper 2 sulfate, you get energy. But when you dissolve hydrated copper 2 sulfate, you need energy. Why do you think that is so? Right? And I know some thinkers have already said that when you form the hydrated copper 2 sulfate, that is from the copper sulfate, now you hydrate it partially, add some water molecules, so you get the hydrated copper 2 sulfate. Some energy is of course going to be produced. Some energy is produced. So now you later on you want to hydrate that. Some energy was produced already when you formed the the copper sulfate, the hydrated copper sulfate. Now, so the amount of energy is going to be produced by further hydration is going to be very low. So but you still have to break the copper sulfate apart. So what there is that the lattice is intact. The lattice is intact, but some hydration has already been given off in forming the copper sulfate. So you are going to get very little energy when you hydrate the pentahydrate. Very little energy is going to be produced, but you still need a lot of energy to break the lattice energy. As opposed to when you dissolve the copper sulfate, you get a lot of hydration energy, because you are not given off any. But now, so that is going to be more than the lattice energy. So you discover that dissolving copper sulfate hydrated is endothermic. You will need energy. But dissolving the anhydrous copper sulfate, some energy is going to be given off. Now, so let us continue to see how we can use that. Therefore, the Hess law can be used to calculate enthalpies of solution. Now let's look, for example, at the dissolving of potassium chloride. That is the example that I have decided. Now let's look at that. Now, when I dissolve copper sulfate, I've said I can visualize this process to be taking place in two steps. So I can get the potassium chloride in solution and just add a lot of water. I get potassium aqueous plus chloride ions. What is that? That is what we call the enthalpy of solution. That is just dissolving. Just get the potassium chloride, add a lot of water to make an infinitely dilute solution. So I'll get the potassium, and so it has already dissolved. Alternatively, I could first break the potassium chloride into constituent gaseous ions. That is potassium ions plus the chloride ions in gaseous state, So what is this? That is lattice energy. Of course, the opposite of lattice energy. The opposite of lattice energy. Then after that, I can go on to have this interacting with water. And that is what I've called the hydration energy. So dissolving a substance can be visualized consists of two processes. The dissolving completely. That is the first way in which you can dissolve this substance. The second way, first break it into constituent gaseous ions, lattice energy, then hydrate the constituent gaseous ion. What is the relationship between all these? Now, where are we starting from? This is the initial, and that is the final. This is the intermediate. So what's the relationship? From initial to the final is the same as from the initial to the intermediate to the final. So we've given these enthalpies, and I can put them. So lattice energy of potassium is negative 690. Negative 690. Very wrong. Very wrong. What makes that wrong? Because this is a bond breaking process. Therefore, it should be positive 690. So remember, this one is given as negative because it is the enthalpy of the reverse. But that's not what I'm doing. So you have to be very careful about that. Yeah, so you change it to positive. Then the hydrogen is of course negative. For potassium, negative 305. For the chloride is negative 384. And we can use that and get the enthalpies. And I've already done that. You can have a look at what I've done. So I've drawn the energy cycle. I've said this is equal to the alternative. So positive 690 is equal to, then I've added this is just arithmetic. And that gives me 1 kilojoule per mole. If I must write the thermochemical equation, KCl solid plus aqueous to form potassium aqueous plus chloride ions aqueous, delta H is equal to negative 1 kilojoules. I don't have to indicate per mole. 1 kilojoule. It is for that particular equation. So can you draw an energy level diagram? That's an endothermic process. and therefore we know how to draw an energy level diagram. Now, another example is right there. You could pause the video and attempt it. Pause the video and attempt that. Yeah. And that's the way I got it. Welcome back. I hope you paused and I hope you're getting negative 248, 24, 84, 89.4 kilojoules per mole. It's a lot of energy. So we were asked to get we wanted to get the lattice energy. So what did I do? The dissolving calcium fluoride can be done in two steps, in two ways. I can dissolve it directly. That is the enthalpy of solution. Right? Now the alternative one will be first supply lattice energy to give me that N2 fluoride ions. Let's make that correction. Then I hydrate them. I think if you got it wrong, you must have done the way I did. But I remember to multiply that by 2. That is the only trick in this question. That is the only thing that may make you get it wrong. If you forget to multiply because that is 457 kilojoules per mole of the fluoride ion. But you are now hydrating 2 moles of the fluoride ion. So that needs to be multiplied by 2. And then at the end of it all, I got that as the lattice energy of the calcium fluoride. Now the other thing that we can do is get the enthalpies from empirical data. And I have an example here. What is the heat of solution of sodium hydroxide when 8.8 grams of the solid was dissolved in 1 liter of water at 26.5. The final temperature of the mixture rose to 48 degrees Celsius. You could pause and try to wrestle with that. But before you start, I'll only make one piece of reminder. I'm using 8.8 grams of the solid. Ignore solid. That is what we said when we discussed the enthalpy of displacement. If there is a solid, just ignore it. So if you ignore that, then you'll be able to get the final answer. So you can pause and do it. And welcome back. So heat check during the process MC delta T. M, what surrounds the thermometer? The $1 million question. What surrounds the thermometer? 100 grams, 1,000 grams of water. Why? Because I ignore any solid. So that 4.2 times that's what I decided to use. Cancel the G and G, cancel the K and K, and this is supposed to be capital K. The K and K cancels, so the answer will be in joules. I had divided by 1,000 somehow, so that I get the kilojoules. How many moles of sodium hydroxide have been used? 8.8 grams, so those 0.22, and that is the amount of energy that is produced. It is negative because there is a rising temperature. You got that? Mtoto mwema wewe. Let's continue to another example. Calculate the final temperature of a solution obtained by dissolving 4 grams of ammonium chloride in 100 cubic centimeters of water at 23.5. The enthalpy of solution of ammonium is that much. Again, we are at liberty to pause the video and work out that. Right, I hope this is what you did. You got the amount of heat change. The heat change is 100 grams times 4.18 times delta T. Okay, the energy is going to be in joules. Energy is going to be joules. I have an unknown here, so I cannot get the heat change. So what do I need? I need at least one other thing, in which case I can get the heat change. How do I get the heat change? Working out the number of moles of ammonium chloride. Yeah, we know the 1 mole of ammonium chloride is that. So what about 4 grams? Is this number of moles? But if you dissolved 1 mole of ammonium chloride, 25.8 kilojoules will be absorbed. It's endothermic. I don't need to look at that at the moment. So what about if it's this number of moles? This amount of energy would be absorbed in small k, capital J. Let's always remember that. It costs you a mark. So that now I have these, I have the unknown that I didn't have. I have one other, the known now. I have only one unknown. I can get the delta T to 4.61 Kelvin. Now I subtract that from 23 Kelvin, so whatever I get will be in degrees Celsius. I hope again that is what you've gotten up to. If you have been following all the previous calculations, this should be easy peasy. I know a bit of it. Right, now the next thing we will do is to experimentally determine the enthalpy of solution. In this case, we shall do the enthalpy of solution of potassium nitrate. Now, what will I do? I will get some 3 grams of potassium nitrate. Then I will dissolve it in 30 grams of distilled water. But this is a procedure I will adopt. I will press the 30 cubic centimeters of water in a plastic beaker. Plastic, you know why? Then I will take the temperature of that solution, the initial temperature and the temperature every 30 seconds for 1 minute. After 1.5 minutes, I will add the potassium nitrate. I'll continue to record the temperature every 30 seconds and I will complete the table. So what do you think? What have I said? I will take this initial temperature and I can take time and read these. Read the temperature at 0. Because some people have the tendency of writing a 0 there. It's 0, therefore it is just 0. No, please take that reading. Then I'll take the reading at 30, take the reading at 60, but at 90, I will take completely no reading. Instead, I'll add the solid, after which I will continue taking the reading up to the 4th minute. Looks like the 4th minute is what will be required there. So that has been done, and all you need to do is to record the data and come up with some table. In this experiment, the enthalpy of solution of potassium nitrate is going to be determined. We are going to take the readings every 30 seconds for 2.5 minutes. For 1.5 minutes. After that, we shall add potassium nitrate and shake and still continue to take the reading every 30 seconds and record in the table that is provided. So we start now. You can actually take the reading even before we start so that you can record at time 0. Record that reading corresponding to time 0. Then we shall take the reading every 30 seconds. Remember, after 1.5 minutes, you not take a reading. Instead, you'll add the potassium nitrate. Now, but what do I have? I have 30 cubic centimeters of distilled water, to which I'll be adding 3 grams of potassium nitrate. Remember, that is at 1.5 minutes. So I hope that reading is captured and we can start the watch. So I don't know whether it would be necessary to star. You can decide for yourself whether you are going to star or not. But we shall wait for After that, I expect you to draw the graph of temperature in the vertical axis against time in the horizontal axis. So let's meet when you've done that. You can stop the video, do all that, and then come back. Right, and that is the data that I obtained. Compare your data with mine. I know there will be a small difference again. The small difference will be at that point. Because if I remember very well, from the experiment it was 18. It was 18. But now, we always put an X in that. Now, when you have the X experiments, as we call them, that X should be taken very seriously. Now, two things about that X. Number one thing, the temperature immediately after the X must be the lowest for an endothermic process. Can I say that again? The temperature immediately after the X must be the lowest for an endothermic process. It must never decrease from that. So although I got 18, I had to do something about it. I'm not telling anybody to cheat. I did not tell you. I did not say that. But that temperature must, if it is endothermic, that must be the lowest. If it is exothermic, that must be the highest. Otherwise, you are going to lose the trademark. You're going to lose it. That must be either the highest for exothermic or the lowest for the endothermic process. That is one thing about the X. Number two, the curves will always meet at X. That is the second thing. Extrapolation must be to the X. So you see the way I drew the curve. This is the last plot I have. I've extended to the X. This is the last plot I have. I've extended to the X. So that the X experiments, take note of that. They should be. Now we consider this reaction to be instantaneous. They should be instantaneous. But there is what we call thermodynamic inertia. Thermodynamic inertia. Like the reactions are not, they are taking some time, although they should be instantaneous, but there is some bit of inertia. So that's why we extend there. We expect the reaction to end at that point, but it really doesn't. That is the theoretical point at which the reaction. So we are extending at that point. So the temperature, even if you had made, you did not take a reading here. You didn't take a reading here, but had you taken the reading, it should have been lowest. It should have been lowest because that is when the reaction is over. But only that you waited until the time. By the time you are getting to the 120, it had already cooled a bit. That's the way it had already warmed a bit in this particular case. So know that we are extending to the X. We extend. So the X reactions extrapolation is towards the X. I don't want to say much about filling that table. We have said quite a bit. You can refer to the other subtopics. The decimal, the accuracy, the decimal, the completion of the table. Ensure that you do it. If you don't do, we have ways of knowing that you don't do, and we penalize. We penalize anything that is not really done. Then there is a trade. I was expecting the temperature to remain constant. Why? There's nothing that is being done here. Some people force it. When you leave water, if I leave some water in a karai or in a basin overnight, and then you are telling me that if it's at 22, it will raise to 23, it will get to 24, it will get to 25, it will get to 26. So that means that if I wait long enough, wake up in the morning, I'll take a hot shower. Hey, that's easy, eh? So the water will have even boiled, eh? So because if it is rising, what is making it to rise? It should remain constant there. You are doing nothing. It should only change after the x. Eh? Now using the graph to determine the change in temperature, we always say that you need to show. Always show how you arrive at that. I did show using a dotted line, and I got 5.75. Got 5.75. You could have read it to 5.8, but if you did show, then you still get the mark for showing. Now the change in temperature, MC delta T. Remember, I ignore any solid. So it is that the mass of the water is 30, and then I get that much. Enthalpy of solution. Now this is for how many moles of potassium nitrate? That's it works out to 0.0297 moles. That is what gives that amount of energy. So 1 mole gives that 24. Okay, absorbs. Not that it is endothermic. Why? The temperature is decreasing. Temperature of the surrounding decrease from positive. So kilojoules per mole. The theoretical value is that. Why are they different? Loss of heat to the surrounding, the containers. The assumption that C is equal to that of water, C density is equal to the density of water. Those could have led to the differences. We can wind up this subtopic and by extension the whole of this topic by looking at that particular example. Just copy the example and take some time to attempt it.